Yeah, there we go. Right. We need to finish off proof. Okay, so I am going to run you through a thing called proof by induction. Are you guys happy enough if I write all joined up, or do you want me to write in block capitals? I don't mind either way. Writing up joined up is slightly faster for me, just slightly. Do you mind? Joined up's fine. Sweet. That makes my life a bit simpler because I'm going to drift into it anyway. So proof by induction. All right. Now, this is basically the point where algebra stops becoming a tool to solve a problem and starts becoming a language. So you're beginning to now drift into the world where your algebra skills are going to just be assumed. And if there's anything you're not sure about, and the notation gets really screwy and all those things. So anything you're not sure about, you need to ask and take your time, all right? So let's have a look then at a nice example. A nice example. Okay. So if I had sigma 2 r minus 1 r equals 1 to the n. Have you seen anything like that ever before? Not really? Okay. 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 Well, let me just do an aside. If I just had sigma r equals 1 to the n of r, all that would mean is I would have 1, where r is 1, add 2, add 3, add 4, add 5, all the way up to n. So what happens is we sum from r equals 1 to n. Now, if I had said we're going to k and we'll start with x equals 3 of x squared, say. So that would be 3 squared. So we started where x equals 3 plus 4 squared plus 5 squared plus dot 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 all the way up to k squared. Okay, so it just lets us add together a range of things. Does that make sense, Lucas? The symbol's called, yeah, the symbol's called sigma. It's a Greek letter. The other one that you might come across is, say, r equals 1 to k of r plus 1, say, for the sake of argument. So if the big sigma symbol means add, Alex, have you seen the big pi symbol before? No? It just means multiply. So that would be 1 plus 1 multiplied by 2 plus 1 multiplied by 3 plus 1, yeah, and so on, all the way up to k plus 1. All right, so you might see the pi one crop up from time to time, but the main one that you'll see at A level is the sigma symbol, and that just means sum of. Okay, so the sum of 2r minus 1 from r equals 1 to n. That's how we would describe that. Okay, so what we're going to do is we're going to prove by induction from r equals 1 to n that 2r minus 1 is equal to n squared. So really what we're saying here is that we can build n squared by adding together all the different components. So induction has 4 steps. 4 steps. All right. What we do is we start with an example. We start with the very basic example. And usually what we would do is we would look at where we start. So we start here at r is equal to 1. So we're just going to do that. We're going to let r equal 1, and this is part 1. This is so step 1 is an example, and this is a really important step, and it'll all become clear now at the end what we're doing. So what we'll say is 2 times 1 take away 1 equals 1 squared. So again, it's really important that whenever you're substituting something in, you're sticking it in a bracket, because it makes it really easy to keep track of where you're substituting stuff in and everything, so you don't get muddled up. So 2 times 1 take away 1, well, that equals 1, and 1 squared is equal to 1. So yes, that's true. So what you'll see is me writing little annotations and things like that. They are important. All of that is important. It needs to be in there. Step 2 then is our assumption. So what we're going to assume is that this is, so our assumption, we're going to assume that sigma r is equal to, r is equal to 1 to k of 2r minus 1 is equal to k squared. So we're going to assume it's true for some value k. Okay, we're going to assume that it's true for some value. We've shown it's true for 1, but we're going to assume then that it's true for some value of k that we don't know about, nor do we care about at this point. Okay, then we're going to do the inductive step. Okay, so this is the inductive step. And if it's true for the value k, then it must be true for k plus 1. So what we can say is that sigma of r equals 1 to k plus 1 of 2r minus 1 must be equal to k plus 1 must be equal to k plus 1 squared. That must be true, but let's try and show that's true. So we need to show, this is important, we need to show this is true. That's what we're trying to show is true. So in order to do that, what we need to think about is how do we get from n equals k to n is equal to k plus 1? How do we actually do that? So let's have a look at our thing. So we've got sigma of k, r is equal to 1 of 2r minus 1. And we've got sigma r equals 1 to k plus 1 of 2r minus 1. Okay, so these are two different things simply because this one on the right hand side has more terms. It has one more term in it. So this one here is all the gubbins, add 2k minus 1, take my k in brackets, and this one here is all the stuff, and then we're going to have 2k minus 1, and we're going to have 2k plus 1 minus 1. Okay, does that make sense? Or have I lost you? That's a really important piece of... Alex, you're happy? Lucas? Sort of makes sense. Okay, this is really important. So we just need to nail this one down. So this, on the left-hand side, this one here, that summation only goes as high as k. The biggest number it has in it is k. So it ends with 2k take away 1. Are you happy with that, Lucas? That's the last term in that series. Yeah. Now, this one over here on the right-hand side, let's change color so we can... This one over here ends at k plus 1. Okay, so it ends at a bigger number. So the last two terms of it are going to be 2k minus 1 and 2k plus 1 minus 1. Does that make sense? Yeah. Okay. So all we're thinking about is how do we get from the left-hand side to the right-hand side? Well, all we do is we would add on, we just need to add on that term there. Okay. So we can say then that k plus 1, r equals 1, 2r take away 1, that is equal to the sum from, let's do better, sigma than that, sigma k r equals 1, 2r take away 1, and we just need to add on to k plus 1 minus 1. So I'm just going to add this bit on to make, so those two are equal. Are you satisfied that they're equal? Yeah, okay, cool. Okay, now we need to have a look at this boyo here, that boyo there. Using our assumption, what was our assumption? Well, our assumption was that the sum from r equals 1 to k of 2r minus 1 is equal to k squared. So we can swap that out using our assumption, sigma r equals 1 to k of 2r minus 1 is equal to k squared. So what we have then is that the sum from r equals 1 to k plus 1 of 2r minus 1 is equal to k squared plus 2k plus 1 minus 1. All right, so I've used my assumption, and that then is equal to, so that's going to be k squared plus 2k plus 2 minus 1, which is equal to k squared plus 2k plus 1, which is equal to k plus 1 all squared. So the sum from r equals 1 to k plus 1 of 2r minus 1 is equal to k plus 1 squared. Why am I in the dark? There we go, that's better. Is equal to that as required. Now, let's think about what that means for a second. So at the very start, we showed that it was true for number 1. It was true where n equals 1. And then what we showed is that assuming it's true for some number, it will be true for the next number. So that what that means is that if it's true for the number 1, then it's going to be true for the number 2. And if it's true for the number 2, then it's true for the number 3. And if it's true for the number 3, then it's true for the number 4. And if it's true for the number 4, then it's true for the number 5, and so on. Yeah, so what we've shown is that because it's true for the first one, it's true for the next one, then it's true for every one.